So here is a classic optimization problem. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field bordering a straight river. They don't need any fence along that river. What's the dimensions of the field that this farmer can box off that has the largest area? So a little contrived, a little simplistic maybe, but that's exactly the kind of problem that we need when we're first starting to learn these skills. So I want to take this problem and I want to understand the things that it's talking about, at least those things that can be quantified, right? If I run into, what is the mathematical treatment of what a field is? A little bit above our pay grade for right now. So it can be very helpful as we go about to just sketch some pictures. Or if you don't draw pictures, then just to imagine what's going on. Again, visualization is a very powerful tool, whether it's visualization in your mind or just a little sketch on a piece of paper. It doesn't have to be anything fancy at all. So here are a couple different diagrams of different fences. Each one of them has a perimeter of 2,400 feet. Each one of them is a rectangle with an open side here for this river. And I can figure out that depending on how I've built the fence, I do get a different amount of area inside of that fence. So for this first diagram, we have an area of 220,000 square feet. Seems like a lot. For this second fencing, we've got an interior area of 700,000 feet, so quite a bit more. But if we keep making this field narrower, we'll have an interior area. In this picture, we've got 400,000 square feet of area. Oh, so that's definitely less than what I had before. So how can I build this up as a model? What are my fundamental variables here? Well, I'm most concerned with the area of this region, of this rectangle. We'll just call that A. And the area A depends on both, how wide is this field and how tall is this field? It actually depends on two variables. So here we are using X in the diagram to stand for how tall this field is. Tall, at least from the perspective that it's been drawn. And Y for the width. So the area is just going to be X times Y. Well, that's handy. That gives me things that I can actually quantify and use mathematics on. Now, I do have this problem that it looks like I've got two independent variables. However, there is a constraint. I don't get to just pick my X and my Y to be whatever that I want them to be. My X and my Y together need to represent 2,400 feet of fencing. So again, a little contrived, but whenever you work on an optimization problem, you want to understand the constraints of your problem. What are the real world things that are tying us down? Why can't I just build a field as big as I can? Because I don't have infinite fencing. Now, what I can do with my constraint is, because 2x plus y must equal 2,400, Well, that's just an equation. That's an equation with two variables. I can use algebra and say that if this equation must be true, then it is also true that y equals 2400 minus 2 times x. So we'll just say, let's have x be the independent variable, and y will be a dependent variable, right? Once you pick your x, you've automatically picked your y. No other choice. Well, that means that my area function, and it is a function now, pick an x, you get a different amount of area. How much area do I get if I picked some x? Well, I'm going to multiply x by 2400 and then subtract 2x squared, just like it says in my formula, after I've replaced my y by this expression, because my y must be equal to 2400 minus 2x.